6 minutes, 7 minutes, 8 minutes, 10 minutes, yeah, People quite angrily going, no, that chair is saved, you can't have that one. Sorry. Are we on time? There we go. All right, take a seat, everyone. We're about to begin. Here we are, Thursday afternoon slot, the best slot of the whole conference. This is factually going to be the best talk you've ever seen, possibly in your entire lives. Here we go, welcome. So this is Anna Przeborowska. And I practiced it, and I didn't quite get the V at the beginning. And she's going to be talking about music transcription. You've given her a big hand already, but do it again and enjoy the talk.
Hi everyone, I've just found out that I have 5 minutes less than I thought I do, so I'm gonna rush, I guess. Hope it's fine. My name is Anna Przeborowska and I work as a software developer in the music industry in a company called Ableton. At Ableton we produce 3 main products. The main product is a big software. It's a digital audio workstation which allows musicians to record, edit and produce music. Apart from that, it was actually designed as an instrument that you can take on stage and perform live, hence the name. Next thing is Link. Link is a technology that allows people to play together on electronic devices thanks to syncing them in time over a wireless network. And last but not least, this shining beauty is actually something I work on at Ableton. This is an instrument that allows you to create your musical ideas without looking at the computer, although it's connected to life. Yeah, but let's get back to the topic. So what does it mean to transcribe music? Transcribing music means transforming the audio recording to a music notation. What means you just like write down what you hear with notes that can be interpreted by other people. There are some people who have like superpowers of doing it on ear. I'm not one of them. My ears haven't been properly trained to do it, so that's why I prefer to figure out how to teach my machine to do it for me. So let's have a look on what we need to do to perform that. So first of all, we have to figure out how to read the audio stream. We have to think of what it is, what it's going to be, and how to read it and store it so that we can later process it. Then how to figure out that the note actually occurred and what note it was it like C, was it E, what octave it was, and then transcribe it. So write it down in some standardized way that could be interpreted by other software, other electronic instruments, or even other people. Okay, so let's go in steps. First question, how to read and store data. First of all, we need to know what data it is. So our audio input is basically a continuous wave that we unfortunately can't just like process like this with our computer. First, we need to digitize it, of course. Digitization comes into steps, sampling and quantization. What does it mean? So sampling basically changes the signal to a sequence of samples. So we end up having a finite set of samples. How many samples? This is determined by a sampling rate that we choose. So sampling rate defines how many samples will be peaked per second. There is also one important thing that we need to remember of while sampling, which is like one of the basic and most important things in the whole digital signal processing, which is so-called Shannon or Nyquist or simply sampling theorem, that says that you have to make sure to be able to later restore the continuous signal we had on our input. To be able to restore it, we have to make sure that our frequency components in our digitized signal don't contain frequency components above half of the sampling rate. What does it mean? Like what happens if you have like higher frequencies in there? Then this frequency comes in and wants to represent itself in our sample data. So what it does, it tries to assume a different frequency than its own, which is called aliasing. So it kind of takes an alias and like totally affects itself. Aliasing is like a double curse, because first of all, of course, we lose the high frequencies, but we also corrupt our low frequencies, because we don't know anymore if the frequency we have there is actually the one that belongs to the original signal or is there because of aliasing. So yeah, just make sure you pick up the right sampling rate. The usual one is 44.1 kilohertz, and it allows us to basically encode everything that's audible for human being, because we hear something in the range from about 20 to 20k hertz. Okay, then, so now we have our independent domain that contains a finite number of things, like finite number of samples, but now still our dependent variable, it's not finite yet, because each value can be any float. So, but let's say we want to encode our information on set number of bytes, let's say 8, and we want to have only like 256 numbers available for encoding data, which means we have to quantize the data. The most simple thing to do it is just to find the nearest quantization level, so the nearest possible value to assign to a sample, so like just correct the amplitude a bit. So both sampling and quantization end up like restricting how much information we end up having in our digitized signal. Okay, so we know what we have when we read our audio stream. It's going to be like probably rather large array of data. We'll have to figure out what things to choose to, like what data types to choose to store it. And then what we want to do, we want to detect nodes. So first of all, we want to say, okay, the node occurred. We here have a plotted recording done on this wonderful thing. 2 seconds of it, we can see exactly like, I just played 2 notes, right? It's quite easy to see on a plotted waveform. We'll have to figure out how to calculate that. Okay, and then we know that I played 2 notes. Now in a spectrum graph, we can see that these were different notes, right? Because there are significant peaks in different frequencies. Okay, and last step is to think about the standard, how to encode our nodes so that other software understands that later. And let's get our questions again. We need to read and store data, figure out how to do that, how to detect nodes, and how to represent nodes. And before we go any further to my suggested implementation of that, let's see what we're aiming for. So the demo time. And a million things can go wrong right now because it's an real-time audio processing. I'm sure it works, but just a small caveat, ghost nodes may appear due to all the noise around, but let's see how it works. So I'm gonna play this beautiful thing that's been with me ever since I was in elementary school probably, and I'm gonna use it one more and probably last time in my life. I have this microphone here that I'm gonna play to. And I'm not going to play fancy melodies. I'll tell you later on, just single notes. Okay, let's see if it works. So I'm going to ask my algorithm to detect a note, detect its pitch, and play it with a different sound. Let's see how that works. Okay, that was a ghost note. Kinda. You get the idea. Okay. Still better than expected. All right. So what happened here is that we read chunks of data at a time and we processed them, trying to figure out if a node occurred and what node it was. Then we created a node in the standardized format, send it to the synthesizer that produced a different sound, the sound of a piano. Okay, so how did we do that? I read the data using a PyAudio library, which is basically, these are Python bindings around port audio, which is like a cross-platform library enabling you to play and record audio in real time. It supports blocking and non-blocking mode. Non-blocking mode is based on just calling callbacks in a separate thread. That's what we're doing here. So you basically need to instantiate a PyAudio object, create and open a stream, in our case for reading the data. Tell it what data format you want, how many channels you're going to read, and what is the callback. And most importantly, you need to start the stream and make sure the main thread doesn't die, doesn't terminate. You know, so we need to keep it alive by like putting some like a sleep there or something. So let's see how what the callback looks like. We receive a data, frame count, number of data, time influenced status flag. Our data is a string at this point, and what's most important, it needs to return the frame count frames and a flag. Status flag tells our stream if it should continue feeding the data. It happens when we pass PA continue flag, or if it should terminate. In that case, yeah, we put a flag to say PA complete. Stop doing this. Okay, what's next? Next, we have to figure out how to store our data, because like as here we're getting strings, not the best type maybe for data manipulation and calculations, I think. Yeah, so the data is string here, so that's why we convert it to a NumPy array. Why NumPy array? Because it's like hell more efficient than Python lists due to internal implementation, even though both implementations are in C, like just because Python lists allow you to put like different type of objects in the same list and it needs to store the information about the type. It can't really use the vectorized C implementations, hence can't really optimize operations I'm gonna abusively use doing this. Not too efficient. NumPy arrays though speed up things massively. Okay, so, and also like give us for free some rather complicated and cumbersome, but very popular and common operations on big matrices like convolving or like making transposing matrices, or like even we get fast Fourier transform for free. Okay, so now we read our data. Now we want to see if our current chunk of data, something changed and a node occurred. Here, I plotted short-time Fourier transform of our recording from previous example. What does it mean that it's short-time Fourier transform? It means that the recording was divided in chunks, and for each chunk we calculated power spectrum to see the energy changes of the spectrum in time. This way we can distinguish if like there was a significant change in our spectrum, assuming like a node appeared. We don't do that in our real-time implementation, because like we analyze each chunk of data at a time, but basically we do the same. We calculate power spectrum of it, and we try to compare it with previous spectrums. So as we want to measure how quickly the power of our spectrum changes over time, we do it using so-called spectral flux, which is basically the difference between the current power spectrum and the previous one. And it's plotted with a green line here over short-time Fourier transform. Okay, so we could find the peaks in here already, but there are some minor peaks that we might ending up finding, and we don't want that because it's kind of a noise. We apply so-called thresholding function, which is basically we choose a number of chunks that we average and multiply by a given constant to make sure and we are like basically only interested in picking peaks that are above the given threshold and the values that are bigger, non-zero values that are bigger than the previous value. In here we can see that thresholding function could be better because it still leaves behind some peaks we don't want to choose. In my implementation, thresholding function like reaches far higher because I wanted to make sure it's not too sensitive in an environment like this. So it probably performs better. But these two parameters, the number of chunks we're going to average, and the multiplier is basically these are parameters that you can change to adapt your, to make your application perform better. Okay, now we picked the significant peaks here, and we want to find what pitch these notes had. We do it by calculating so-called cepstrum of a signal, and cepstrum is an inverse Fourier transform of a logarithm of a calculated spectrum. Easy. In like simple words, it's kind of a spectrum of a spectrum. So that's a way to think about it. And basically you can treat it as the information of about the rate of change over time. So it's kind of a measure of time. You shouldn't think about it as of a signal in time domain, but it's kind of correlated with the time in that, so we all know that frequency equals 1 per time of a single cycle of a wave. So knowing that, in our frequency domain, frequency is a domain of cepstrum, they're all like playing with words, spectrum, cepstrum, frequency, frequency. Frequency is like, it represents like the time cycles. So like the high frequencies will be like have shorter time cycles, and they will be represented at the beginning of a frequency domain, and then the lower frequencies at the end. Here, so before we start picking our finding our fundamental frequency in this cepstrum, we want to actually, this is already narrowed, so we want to narrow the cepstrum to the frequencies we are interested in. I narrowed the frequency to frequencies to ones corresponding to like 8 notes I would probably be willing to play tonight. Yeah, and so it's like pretty narrow range. And we can think of it, so these frequencies are from 500 hertz to 1200 hertz. We can also think about them as narrowing it to 80 microseconds of a time cycle to 2 milliseconds of a time cycle that corresponds to 500 hertz. This is how cepstrum works, more or less. Okay, so knowing this, we picked the maximum value, which in our example was between 25 and 30. And okay, we have the value in frequency domain. We have to now transform the frequency to frequency because that's what we are interested in. To calculate it, we simply divide the sample rate by the cepstrum peak index, which kind of is derived from what I've just tried to explain. So in our example, this is what I mentioned. We are narrowing the cepstrum and then find a peak in the narrowed cepstrum. But then, well, actually, when we are trying to figure out what was the fundamental frequency, we had to remember that the peak index should refer to the original cepstrum. That's what we're doing here. And we figure out, like, saying, okay, it's the value of it ends up being 689 hertz. Okay, now it's also nice to mention that by like pitch detection applies a slight correction to our onset detection, because then we can just ignore the onsets that are out of our the frequency range of our interest. Okay, now we found the notes. Now we want to encode it in a thing that can be later understood by our synthesizer. So what we do is that we choose something ready to use, something like used massively and everything, MIDI protocol. MIDI stands for Musical Instrument Digital Interface, and it basically, it can code like a note and velocity, like the pitch and velocity of our notes. The messages, MIDI messages we're interested in would be note on and note off. Note on means start playing a note, note off, stop playing a note. Message consists of 3 bytes, as we can see here. In the first one, we say what kind of a message it is, what channel we're using. We have 16 channels to use. Second data byte has our pitch encoded. As we can see, it's on 7 bytes, just 128 values. And the last one is velocity, meaning like velocity is the strength of the note being played. So it means like we perceive a note being played louder or softer. Okay, so this is how we transform frequency to MIDI note number, because as we can see, we only have 7 bytes to encode our pitch, meaning the maximum value would be 127, but our frequency before was 689. So how do we encode that? Well, like this. And this is the some part of a chart that actually tells you what note in what octave has what MIDI number and what frequency. And as we can see here, our found note of frequency 698 Hertz is a note F in 7th octave and has a MIDI number 77. Okay, now we know what our note is, what we can encode a MIDI message, and we can send it to a different instrument. I chose a library called PyFluteSynth, which is also a set of Python bindings around a thing called FluteSynth, which is basically software that allows you to play sound fonts that encode instruments in real time. And yeah, that would be it. What are the conclusions? Python is amazing for rapid prototyping. I wouldn't really use Python probably for production code, but to just check out different ideas, solutions, or like even try out different pitch detection algorithms. It works like as a charm. The whole thing that we've seen now, it's not a lot of code. You can have a look. It's on GitHub. It's been on GitHub for the last like 2 hours, I think. So still, the sound font that I use now, it's not pushed there because it was too big. So you'll have to like download your own, but they're available online. It's no problem. And okay, so why is it so good for rapid prototyping? So first of all, thanks to amazing numerical libraries that I briefly discussed before, like NumPy makes things much easier. Hail NumPy. And of course, I/O operations in Python are like really simple, no much messing around, like that's really useful. And the API of the wrappers I used are really good, and they make the code look very clean and very readable. So yeah, that's it. That's all I have had prepared today. And yeah.
Yeah, we do have 4 minutes for questions. This hand went up immediately.
Hello.
Hi.
2 questions actually. First, you need a very good microphone or whatever works?
Microphone?
Yes.
No, not very good, but I just brought this one because the laptop microphone like gets the noise from all around. Like
okay.
Also, that's how it's designed. This one is more like pointing my direction.
And second, what about instrument identification? I mean, knowing that it's a piano or a guitar or a violin or a...
It's a different thing. So distinguishing between, so different instruments would have different spectral features, and then we would need to analyze different things. Like we wouldn't care about the energy distribution over time. We would rather care about energy distribution at all, because different instruments would probably have different characteristics in this. So this would be probably completely different things to analyze, although having similar concepts. Yeah.
So thanks for the talk, it was super good. Quick question, so this is for mono, so if there's like one melody and only one note playing at the same time.
Yes.
What are the main sort of challenges or maybe sort of advice that you might have if you want to do this for chords?
Yes, so the problem with chords is that like it's hard to distinguish what notes were played because the frequencies overlap. And if I had a very performant algorithm now to present on like transcribing chords, I would probably be a PhD by now. And so I'm certainly gonna try out some things, but the solutions available by now are no more efficient than 70%, so it's a rather complicated thing. I still think I'm gonna work and try out different things. A very interesting concept is a CQT transform. You can have a look. This is what people tend to like try to use for polyphonic music recognition as well. So, but yeah, that's why I didn't try it.
More questions. There you go. We had the same question.
You know that there is a story that says that Wolfgang Amadeus Mozart, when he was a child, he heard a full play of a piece of music, and he was able to transcribe from his memory all the piece. Your system is able to hear a full piece of music and print in music notes all the piece, like Mozart?
Well, the problem, this version and this version pushed to GitHub works only for real-time input, so one chunk at a time, one note at a time. I initially implemented it for analyzing the whole like pre-recorded things, files, and so actually it can recognize notes and pitches of it in time and like reconstruct, like create MIDI notes with like keeping the time and pitch and so on. But unfortunately, the problem, as discussed with by answering the different question, would be to like have polyphonic music transcription, which I don't support yet. So that would sadly not work. Maybe in the future, I hope. That's a direction.
We have time for one more question.
I'm thinking about it. So you can make recognition of monophonic music. Do you know about some implementations that also let a user teach the algorithm about something like this is the noise, don't interpret it, or this is my color of instrument, don't interpret anything else. Is it any approachable? Because even in Ableton I see different algorithm for harmonic detection, different algorithm for melody, for rhythm, and no any method for supervised detection. So, is it practical? Is it practical at all, or it would be too difficult to implement?
I'm not sure I completely understand the question. Like, would it be only transcribe one instrument or only?
Yeah, kind of.
Yeah?
Like I could say to algorithm that I want to transcribe this and don't transcribe that. So such to know detect your ghost notes like here.
Yes.
So this is a noise and it interprets it. So maybe you could just put this noise to algorithm and it would learn that it is just noise.
Yeah, so I mentioned before, I think like maybe you would first have to have like kind of instrument recognition, like, you know, like to find out some spectral features that would be able to determine, like, you know, the instrument that you want to sort out or something. Not trivial to implement, I guess. I don't think it's on radar. But it's certainly an interesting thing. I think so. You just probably, yeah, first of all, would have to try out, like checking different spectral features, like what works best for distinguishing between different instruments, like what tracks the timbre or something, and then just apply it as your filter for the pitch detection. That would be my idea of how to approach that, but unfortunately I don't know of any ready implementations like this. there are people who are trying to like separate instruments, and it's the same problem. Like the frequencies overlap, the characteristics are sometimes too similar. So yeah, I don't know of anything that would perform well or would really work.
And that's all we have time for, so I'm sure you'll all join me in thanking Anna Jaworska. Which kind of display have you got? HDMI?
Yeah.
Oh, but yeah, okay, fine. This is an HDMI to VGA. Nice title.
Sorry?
Nice title.
Yeah.
So these on, oh, it's loading.
It's on, because it's on Google Drive, so
Okay, fine.
hopefully it works.
All right, you're happy like this, duplicate size and image?
Yeah, it's fine.
You haven't got any audio or anything complicated?
Nope,
That
nope.
makes you easier than that, no?
Sadly only text, so yeah.
Text and a fascinating speaker, let's not forget.
Oh, excellent. Thank you.
You've got a half-hour slot.
I have 45 minutes left, I think.
Oh, great.
I hope so.
Sorry.
Otherwise, we're going to run into a timing problem.
No, you're absolutely right. So 14:30, and you've got this one over here. So, yeah, 45 minutes.
Yeah.
Good. Okay. All right. So the good thing about this, as long as we start on time, you actually get the 45 minutes.
Yeah, okay.
It's slightly unfair on the first speaker. They get cut off short. So how's your time on this? Do you want 10 minutes for questions?
I think 5 minutes of questions is all I have time for. So yeah, if you could just give me the heads up of
That's
that.
fine.
I'm going to try to go fast, but as you have kind of like a lot of material, so
Okay, fine. So shall I give you a warning at 15, 10 and 5?
yeah, that would be
And the
super.
5-minute warning means it's 5 minutes until questions.
Okay, that would be super. Yeah, that would be excellent. And
So
you're
15, 10,
Harry. Thanks so much, Harry.
I should interest you as Catherine John Moore.
Yeah.
Is that correct?
Yeah.
And should we say, there you go, talk to you about machine learning. Catherine John Moore hates your computer.
And my computer too. The equal opportunity computer. I mean, we all have to be like we're all like that. Sometimes, so.
I look forward to it. I'm very glad to be
Awesome,
sharing this room
awesome.
today.
Oh, cool. Yeah, this whole track looks awesome. I wanted to go to the last one, but I was like, I should just relax and work through my slides.
You wouldn't be able to really listen to it all when you're thinking about it.
Right? Yeah, it's the worst. So.
You can see it online. The most amazing thing was the live demo, which, this thing was going to fail, and then it actually works.
Oh, that's awesome.
All right. Settle down, children. Settle down, settle down. There you go. Anybody that's leaving the room, please now leave the room quickly and quietly. There you go. Have a seat. Welcome to the second after lunch talk of the Thursday of the conference, which is always the best talk since the last best talk. And I'd like you to all join me in welcoming Catherine, because Catherine hates your computer. Give her a hand.
Hello, and I wanted to start by thanking everybody for coming here, thanking Europython for having me, and thanking the Europython Social Verein for hosting a really great event. I've had a wonderful time, and I keep meeting people way smarter than me, so that's always a good sign. My name is Catherine Jarmel. I'm known across the internet as KJam. I run a company called KJamistan, so you can find me blogging and writing and talking about things at kjamistan.com. And I like working with text and data. And if you're ever in Berlin, come by the Pi Data Meetup group. We're a fun group of people, and we'd love to meet you. So I feel like because I'm talking on machine learning and I don't have a PhD next to my name, I need to have this disclaimer slide, which is I am not an expert in machine learning. I can't sit here and tell you about which algorithms work better and exactly why. I'm a Python developer and I'm interested in applying machine learning to text analysis and sentiment analysis. So by all means, if you are a machine learning expert and I say something wrong, feel free to either correct me in the questions or I will buy you a beer later and you can teach me something. So here's some assumptions I've made about you. I'm not going to be going over NLP basics. I'm not going to be going over machine learning basics. I assume that we already have those covered. If you want to talk about basics later, then again, of course, happy to talk about it later. But I'm assuming that you already have done maybe even a little bit of sentiment analysis, but you already have played around with some natural language processing, and you have some basic understandings of machine learning and what methods to use. So here's a little bit of what we'll cover. In the initial description, I said that there was going to be live coding and demos and this and that. Upon further inspection, that becomes a little bit more difficult when we go into deep sentiment analysis and cross-language sentiment analysis. So what I'm going to do is I'm going to present you some code and some repositories that are good to use, but we don't have time today for live coding. Instead, we're going to cover some of the tools. We're going to talk a little bit about Watson and how it's being used. We're going to talk a little bit about sentiment analysis, and we're going to cover a lot of the research that's being done. Right now, I'm seeing a massive gap in terms of the research that's being done around sentiment analysis and the tools we have available in code. And I'm kind of hoping to push forward the conversation in the Python community by giving this talk and kind of covering a little bit of what's happening. So what we won't cover is some magical Python library where you can download today and it works in multiple languages for sentiment analysis. I must say that if you want to take a look, please send hate mail to Salesforce. So in case you wanted to send hate mail somewhere or you want to practice natural language generation and send hate mail somewhere, send it to Salesforce. MetaMind was a really amazing startup using matrix vectorization recurrent neural tensor networks, and they had an open API and it was fabulous. And then Salesforce bought them and they shut down the API and they're currently shutting down the paid API as we speak. I ran into a guy who works for Salesforce who actually gets to work with this team, and I asked him, I begged him, please let something be publicly available, and he said, good luck, have fun with that. So again, all the hate mail, and if you work for Salesforce and you can somehow get me inside the internal network, that would be great. So another one that's trying to do some things, and they're one of the only ones that's available via APIs, is MonkeyLearn. And so here you can see that they have these different modules available. They have some that are being actively worked on. You can also create a publicly available module here. So if you absolutely need, hey, KJAM, like I need something that works tomorrow, I would start at some of these places. But we can see just even looking through the API that we have very different precision levels. And so I would say that's why I'm giving this talk, is we're going to talk about some of the methods and the theory behind how to create a sentiment analysis that works for you. So to begin with, we're going to talk about what is sentiment analysis and how do we go about it in Python. So what is sentiment analysis really? And when I look at this tweet, and I, being American, some of my tweets in my Twitter feed are very American references, so forgive me for being that way. But when we look at this tweet, we have a lot of different sentiment, right? If we look at the emoji, we see crying. If we look at the photo that we have here, then we see a different emotion of crying. If we look at the text, then we might just see the word like and determine that this is a positive analysis. And so when we're talking about sentiment analysis, we have all of these different things. We have stance. How does the author feel towards Jennifer Hudson? How does the author feel towards the BET Awards? These are really complex things, and we think we can boil them down into positive, negative, neutral, but I am here to debunk that myth today. So sentiment analysis is used in all different sorts of systems. And I've had the pleasure of going to a sentiment analysis symposium recently and hearing just how many different places it's used. There are even people using it in anomaly detection, and they're charting sentiment across reviews or Twitter, and they're looking at it via release tags. And so there's all different ways that people are using sentiment analysis, including in obviously just simple user satisfaction or brand engagement. So when we look at the sentiment analysis steps, can basically be broken down into 4 major steps. And they basically go from left to right and top to bottom. However, depending on what you choose, they could be mixed up. So the first thing is dealing with your corpora. Are you building a lexicon? How are you using your labeling? Next, then you're probably going to choose your algorithm, or you're going to determine what model or approach to use. Then you're doing parsing and pre-processing. You might even do normalization and standardization across your data set. And finally, you're testing, evaluating, and improving. And in that improvement step, you may revisit any of these earlier steps. It's quite possible that you will need to improve your model. So we're going to go through the talk and we're going to basically cover all of the steps, and we're going to talk about what's happening in research and what's happening in code. The first step is choosing your lexicon. So one of the oldest and most tested and true ways of auto-tagging a lexicon, particularly if you're using social media data, is auto-tagging. And it's this idea of distance supervision. So I'm going to go and I'm going to gather tweets, or I'm going to go and gather Facebook statuses, or whatever I'm going to use, and I'm going to map with emoticons or emoji. And you can think about this also as a good opportunity to use a thesaurus. So in quite a lot of the research, they will also just expand the corpora that they're using by using a thesaurus. So I want to grab all hashtag happy, hashtag joyful, etc. And this can also help expand into new languages. If you're working in one language and then you want to apply a different model, as long as you have a very good thesaurus, then you can do that. Then one of the other steps that you're going to need, so now you have all of this data, how do you tag it? We have this very naive idea that everything can be tagged positive, negative, or positive, negative, neutral, or even positive, negative, indeterminate, neutral. That's really, in research, being proven wrong. And so what we have to think about here is if you really need a simple model that's simply positive, negative, and neutral, then you're going to have a lot of gray area, and you're going to have probably more ending up in neutral or more ending up in false positives or false negatives. So when you start moving away from that and you start thinking about positive and negative as a scale, you start to see that things converge a lot faster and that you have less of these false positives and negatives. This also means that you have to build your own lexicon and you have to label it yourself. So there's pluses and minuses, and depending on the resources of your team, you may not be able to do that. There's also quite a lot of people looking at stance detection. So this is a mixture of NLP topic identification or entity detection, and then using stance. And a lot of that right now is essentially a bag of words model still. And people are trying to evolve that to be more advanced and to try and look at things and say, okay, can I determine that these set of words are actually applied to this organization or this entity, and then I can start to detect these stance. So it might be positive towards, I really like this restaurant. It has great food, but the service was total crap. Then that means that I have one idea of the restaurant, one idea of the food, and one idea of the service, right? And then finally, we have this categorization by emotion. Because we have this wide range of emotions, it's really difficult to determine just positive or negative. So in terms of tagging a lexicon, oh, and it looks like one of my emojis is broken, we have a few different methods. So I'll actually start from the bottom. The simple Boolean is 0, 1, right? Or maybe -1, 0, 1. Then we have this sliding scale, which is going from completely negative to completely positive. And I'm asking people then to just rate on this scale. What they've actually found with research on that is that people tire over time. So if you're sitting there asking me to rate something for 5 hours, I'm eventually gonna just be like neutral, 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 and try to get done with it, right? And like we know that just from our knowledge of humans. They also have found that psychologically people avoid the edges. So you'll get much more representative of like, it's kind of negative, it's kind of positive, because people don't want to say it's completely negative or completely positive. So one of the best methods that's recently come into practice is this best-worst scenario. and you have a list of, say, 4 or maybe 5 words or n-grams, and you can use that and you can ask people, say, okay, choose the most positive and the most negative. And that actually is creating some really interesting lexicon, and what they found is that people agree after about 3 examples. So I can show it to 3 people and move on to my next sample, and I'm in the 90% agreement range, which is pretty massive for tagging lexicons. And this is another simple study, and this is somebody, Saif M. Muhammad, who works in the National Resource Council in Canada, does quite a lot of different talks on SEM-Eval competitions, which is like a sentiment evaluation machine learning competition that happens every year. And he has some really great state-of-the-art models. What he found is that when he switched to using a scale of -1 to 1, that 90% of people agree within 0.4 of each other. So that was a really interesting revelation to move away from this 0-1, because we hear constantly, oh, well, humans don't even agree 77% of the time, or whatever statistic you look at. And what he was able to find is when you give people a scale and you let people speak on a scale, you can actually find this least perceptible difference. And particularly then, if you even focus on native language speakers, you get an even smaller, score difference there. So I had the opportunity to chat, and I'll hopefully be posting our chat with William Hamilton, who's currently working at Stanford on his PhD. And he's developed a new model called social scent. And what he's done is he's taken subreddits and he's determined that subreddits and different communities use language differently. So when I'm hanging out in R Sports and I say, oh man, he's really soft, I don't mean that as a compliment, right? I mean that in a really negative way. So again, we have this mentality a lot of times in this code that we all use the same words to describe positive and negative, and that's just not the case, especially if you're doing sentiment analysis on a community, and especially a community like, for example, us as Python developers. We're going to have a lot of different ways that we use words. He has all of his data available, and I took a look at R programming, and I pulled out some of the most positive and the most negative. I also found out that Python has a slightly negative definition. So I know you're all talking trash about Python on R programming, and you need to stop. So here I found some interesting things. It's funny to me that 200 is right in the middle. Like, we can tell that we have web developers in R programming. And spaghetti is really negative, but I love spaghetti. But spaghetti code, maybe not so much. And we find that Minecraft has a great positive association. And so it's a really interesting data set. It's only unigrams right now, but he's very open to suggestions, so feel free to send him any suggestions or ask him to do a certain n-gram for you. So now that we have our lexicon, or we've chosen a lexicon, we need to choose an approach or an algorithm. So how do we do that? What machine learning systems can we use? And it turns out we can use a whole bunch. And I know this is throwing a little bit of a lot on the screen, but there are all different ways that people are using machine learning with sentiment analysis. And they're achieving really great results with really small data sets. So I'll come to this again later, but if you are dealing with movie reviews, you're good to go. But if you're not using the IMDb model or lexicon, you start to enter this space where there's quite a lot of active research and not a lot of agreement on what's good to use, why or why not. And people are achieving very different results with very different systems. Obviously, the finely tuned state-of-the-art systems are still the best performing ones right now. And this is these people that spend all of their time researching and pulling out little details. But we don't have time for that, right? We're probably Python developers first and sentiment analysis researchers next. So I'll talk a little bit about how these are comparing. First, I'm going to talk about kind of the older approaches and the newer approaches. The old approach used to be bag of words, or even continuous bag of words. And I would say, oh yeah, it has mainly positive words, it must be positive. The new idea is to start to use word embeddings and start to be able to use those word embeddings in deep learning models. And by doing so, I have a little bit of more complexity. And I can say, hey, there are these words bunched together. Maybe they are bunched together because they have a sentiment together. That's not always the case. The old way was term frequency inverse document frequency, which is basically a nice way of doing bag of words on a document. And the new way is using these doc2vec, or these document embedding models. The old way is kind of unigrams. If I say good job, I mean good, and I'm talking about job, and they're all related. And the new way is talking about skipgrams or even dependency modifications, which is starting to look at the parts of speech and label the words with parts of speech, because I may mean very different things if I use a word as a noun versus a verb. And the old way is these supervised state-of-the-art systems, and the new way is kind of moving to a semi-supervised approach. So if you're curious about some of the state-of-the-art sentiment features, and I'll post these slides because they reference the papers across the bottom, this is a good summarization, and this is a summarization of, again, Saif Muhammad's model, which has done really well in competitions. And these are all of the different things that he's pulling out as features, and then he's fine-tuning them and analyzing them and pulling out probably more sub-features that we don't know about that haven't been released. But you can see that there is a starting place if you're interested in tuning your own model. But let's talk about what we can actually use as Python developers and what we can use easily. We can use Word2vec and Doc2vec. How many people in here have used Gensim? Okay, so Gensim is this great library, and what it gives you is these word embeddings. Sorry, how many people know about Word2vec and Doc2vec? Okay, super. So it's this idea of representing a word or a document as a vector. So everything is in a vector space, and it can be multidimensional. It is multidimensional, and what you're going to do is you're going to use Gensim, and Gensim can load in these multidimensional vectors and give you a matrix or vector representation of each of your words and your documents. And what this is going to give you is a mathematical way to represent text, right? And this is kind of where text was held back for quite some time, is we didn't have a really good mathematical way to represent text. We were using counters and bag of words, and that's not that interesting. So there's also Glove Python. So there's two different ways to word embed. Everybody talks really a lot about Word2vec, and I feel like there's not enough attention given to Glove. Glove is the Stanford model, and it has a slightly different representation. It uses a weighted model. So Word2vec is basically, does this word appear in a sentence? Then it means it's somewhat related to these other words in the sentence. Whereas Glove is going to say, hey, these words are closer, therefore they might have more of a proximity in terms of meaning. So depending on what word embedding model you use or method you use, you can get really different results. So here we're comparing word embeddings built on Bag of Words 5, which is like a 5 n-gram, like a 5 words around count. Then we have Bag of Words 2, and then we have a dependency, which again is this part of speech. And what we see is, if you take a look at the Florida line, what we see is in Florida with Bag of Words, we get this mixture of other ways to talk about Florida, cities in Florida, but when we move to dependencies, we get other states. And this is maybe significant to whatever you're trying to do. If you want other entities, likewise entities, rather than just related words, you might want to look at a dependency word embedding rather than a Bag of Words word embedding. There's an online comparison tool where you can look at this. And so I took a look at Python, and it looks like there's some of them mixed together. If you use Bag of Words 5, 2, or the dependency, you get slightly different results. And the really neat thing about this is in this as well, they give you a little bit of a visualization of how those word embeddings are used. And so if you want to just play around and start to make decisions on what you're using for your word embeddings, then I recommend going to this site. So another thing that I feel like needs to be raised is it was recently released, there was a paper referenced at the bottom, where word embeddings are not neutral. They're based on human language, and they have the same biases that you would expect to see in humans. And to come up with some of these vectors, I was using the Google News vectorization, the 300 one. And that one is used by places all over the place. And I found some pretty atrocious stuff in there. Maybe not in the first 10 examples, like for example here at the bottom, there was some intense racism going on if I looked at the top 30 words that were within that space. So I forewarn you too, especially if you're using it for something like sentiment, right, which we may have some words mixed in there that are very biased. or if you're using it for natural language generation, then you need to be very aware that these biases exist. One interesting thing, however, is the authors of this paper were able to find, they could find vectors showing the actual misogyny. So they specifically focused on the misogyny in it, and they were actually able to reverse it and reverse the vectors by finding these vectors that were pushing things in a direction where women had lesser professions. So let's talk about what that actually means. Here I have some great examples used. It is too much code to go over in a short talk, so I would recommend looking at them. These are great examples for simple machine learning. So this is using naive Bayes or simple linear approaches, linear SVM. And what it's doing is it's going to take the vector and it's going to chart it to whatever it is, whatever you're using as labels. And if you want to do it in a document approach, you're essentially taking a vector of the document model or the sentence model, it depends, and they have different results. And then you're passing it as a labeled sentence. A labeled sentence is actually a model in GenSum. So if you're using GenSum, you can label your sentences and then pass them directly in, let's say, a logistic regression or whatever it is you'd like to use. This is like a simple approach, right? These are the shallow machine learnings. Another thing to be aware of when you're making these decisions is you're choosing your n-grams, right? So you have to choose unigram or bigram, or how do you want to represent these? And when you're choosing word embeddings, you're generally making those decisions as you're choosing the word embedding. And what they found, this is the research by Stanford, which enabled them to come up with the matrix vectorization recurrent neural tensor network. And what they found is the longer you let your n-grams, the more mixed sentiment you have, which is kind of logical. When you think about it, and I'm going to go on and on and on and have a big long sentence, I'm probably going to express maybe differing viewpoints or a mixed emotion. And so if you're choosing unigrams or bigrams, you can see you're way over here. And there's some words that are obviously negative and positive, but there's probably a lot of words that are just filler words. And the further you go towards exploring the n-grams, the more complex sentiment you get, and the more people are able to say, okay, yeah, this phrase is definitely negative, and the whole phrase is negative. So this is based on the Stanford Sentiment word bank, which is available in Java. Another approach that people are using for this that's going pretty well is LSTM, which is long short-term memory networks. And these are deep learning networks. And what they're using is they're generally using these word embeddings or these document embeddings, and they're pushing them into these deep learning models. And the nice thing about LSTM, and why it's been doing some really amazing stuff for also other natural language processing, is that it can forget things. So it can learn things and it can forget things. So because it has that ability, what it can do is it can change as it sees more or less of a representative model. So language we know changes and trends come and go. And because of that, this approach has been really powerful. And you can use it with both Theano and TensorFlow. I have some examples. There's also the ability to use convolutional neural networks. And so initially the idea is that convolutional neural networks are really great at images because you can chunk and label images and then move accordingly through the pixels, right? You can crop them. But now people are using it for sentences or for documents, and they're able to use the word embeddings for each of those and chunk and move through them. And then through the same principles of pooling and softmax, you can then reach a conclusion and say, okay, according to my sigmoid softmax, this is positive or negative or neutral. And again, I will be posting these so you can take a look at the links. It's a little bit different when you're dealing with deep learning labeled text. So what a lot of times you'll have is you'll have the document, and then you'll be passing an array. And a lot of times people are just using simple arrays like, okay, this is positive, so it's going to point up, and this negative is going to point down. There's different things happening in this, so I would keep an eye on this space in terms of how it performs. Because again, right here we're having this, everything is either positive or negative. I'd be curious to see, and I know that some of the academics are working on more complex representations of the labeling. And because of that this might become an interesting space sooner rather than later. And then here's where a lot of people are kind of using this dual system. Maybe I have a simple classifier, and I have a lexicon, and I have auto-tagging. And I'm feeding them both into a deep learning system. So maybe I have a constant Twitter feed or this or that, and I'm feeding it into a simple classifier, and I'm allowing my deep learning system to learn from that classifier. This is where a lot of people are starting to experience some big jumps without having to do a lot of work. So if you're like me and you're lazy, this might be the best approach. There's still obviously some open research, but it's an interesting theory, this idea that I can just use my simple state-of-the-art classifier and feed it into my deep learning system, and my deep learning system will eventually become more intelligent and have a much wider lexicon over time. So depending on your system, you might need to handle regularization, preprocessing, parsing. This is like the classic NLP problems, right? Is pre-processing essential? It really depends who you ask. There have been some really interesting research on sentiment analysis and saying doing too much pre-processing actually is a problem. And what ends up happening is you get rid of some of this way that we speak in slang to one another, or the way that we use colloquialisms, and by getting rid of those, you actually are removing part of how we're expressing ourselves. So what I would recommend, and what generally the literature agrees upon, is do minimal pre-processing, like maybe just some simple lemmatization or some simple tagging, and then try it. And then do more pre-processing, and then try that. And see where you hit a nice accuracy in your model. And this is kind of where Sense2Vec and Spacey are really making some cool inroads. Spacey is a startup based in Berlin, and they are doing essentially parsey McParser face in Python. And what they're able to do is they trained on, or they have the English language and the German language corpus available, trained on Reddit data. And what they're able to do is they're tagging each of the vectors. So Sense2Vec is you have this tagged vector. So when I talk about Google the organization and Google the verb, I mean different things, and I might feel differently about them in terms of sentiment. So they're making some great inroads. When I pass in, this is using Spacey, when I pass in the vector for the winky face old school emoji, then I get back some of these other things, and I can see that I'm getting back interjections, which is probably a lot more of how we use the winky emoji in the way we express sentiment. Like I might say something that I don't mean, like I hate you computer, and then use winky face to say, I'm just kidding. So here we can see that Spacey is picking up on the fact that I may actually be negating what I'm saying. And I'd be really curious to see how Spacey gets incorporated into a lot of these deep learning models. It hasn't been incorporated in most of them yet. Finally, we get to kind of like what IBM Watson is doing, and we're talking about emotions here. So there's this famous diagram that you see almost at every sentiment analysis talk, and it's this idea that we have all of these emotions, but our emotions can be made down into just these 8 core emotions, and then everything else is just some combination of those 8 core emotions. I am no psychologist, so I can't comment on this, but you know, it makes somewhat sense. So if you're looking into sentiment analysis and you want to start moving away from just positive and negative and you want to move into emotions, let's say you're in charge of like customer service channels and you're trying to say, I really want to know when the rage and loathing are activated because we need to work on that first. But I don't care so much about the positive emotions. I care about more of these angers. IBM Watson has the tone analyzer that's available on the Bluemix API. And it tries to classify into anger, joy, fear, distrust, and sadness. It also has the social tendencies and the language style. So one of the interesting things that I was asking some researchers when I was able to chat with them is, hey, could you maybe say, hey, I'm angry, but I'm saying something positive? That means maybe I'm being sarcastic or ironic. And what the response I got is that nobody's really doing that yet, but that would be interesting to hear about. So I will hopefully be building something that does something similar to this and taking a look at, can we start to talk about when our words say one thing, but our tone, or maybe our tone over time, says another. And by building these models, by even necessarily saying like you as one person have a lexicon and you speak a certain way, can we actually start to understand sentiment at a much deeper level? And we'll get into that as we talk about the next portion, which is what is still unsolved, which is sadly quite a lot. So apologies if you live in the UK and are offended, but I found this to be very funny. But yeah, humor. Humor is lost on sentiment analysis models. We don't know how to tell when somebody's being funny. And we, a lot of times, can't even tell what they're being funny about. So here, I have this mixture, this social media presence, which is this mixture of images and text. And how can we start to, we know how to understand images now, and we know how to understand text. But there's very few that try to do both. And in sentiment, this is a really key part, because how we're talking online is with this combination. So negation is still a really big problem. And here's a unigram and bigram study that says when you negate a unigram or a bigram, the red line is the assumption that you simply create a negative value for that unigram or bigram. And what we see here is the blue dots are the actual representation. So when I say, yeah, it was not that bad, then I don't actually mean that it was good, right? And so we can start to look at these and talk about, hey, it's not so simple to say just because even somebody negates an emotion, it is some opposite. And there's been some really interesting studies about modifiers and how maybe they can point towards a mathematical representation of negation of a sentiment. So back to Stanford sentiment trees, which are these MVRNTN networks. And they actually have gotten pretty advanced at determining negation and overall sentiment of a complex sentence. And what they are doing here is they're creating smaller n-grams, and they're creating sentiment vectorization for that. And then they have a series of logic rules. And the logic rules state, okay, well, this is more negative than this is positive, so overall it is negative. And they're doing some really, really interesting research. Again, they have their Java jar that you can download and play around with. It's still mainly trained on these movie reviews, which we'll get to in a second. So we still have this problem that it's trained on movie reviews. So there's still quite a lot of things that are hard. We have mixed sentiment, we have complex emotions, sarcasm, irony, humor, lost, right? We also have speaker intention and personality, and there's been some interesting research in that in terms of trying to determine who you are as a speaker. And if I study you over time, can I determine who you are as a speaker, and then can I get a better idea of what you mean? We also have slang and like new and older phrases. So part of William Hamilton's study with social scent was looking at sentiment over time. And he was pointing out that if you look at historical documents, you can't use any normal sentiment analysis because in 1920, people were talking a lot differently about things. And we have these new phrases too, where, cool AF means something very different than just cool, right? And so then we also have just general NLP issues. So I feel like I would be left out of Europython if I didn't have a Pokemon reference in my slides. So I put one in here, which I really hope people in America do anyways, because I'm very fearful watching from Berlin about what may or may not happen in November. And so yeah, let's put some Pokemon lures and unleash them in the polling places. But here's an idea. This is obviously exploring a sentiment, but no sentiment analysis would understand this. So when we're talking about cultural references, we also need an ability to say, hey, right now, Pokemon means emphasis. We also have speaking with images and GIFs, right? So now that Giphy is part of Twitter, this is important, right? I would not understand the sentiment of this tweet if I couldn't also look at the image and then determine sentiment of the image. Right? And the really interesting thing is a lot of these are tagged, right? So these are in a tagged database somewhere, and maybe somewhere there's like hashtag hate or hashtag or whatever it is. And I can apply sentiment to these, and then I can pull them out, pull pull out the visual representation and put it back into words and use those words to make a decision. Another really big problem with these is speed and memory. So if you ever try to make your own word embeddings, like I hope that you have a server somewhere set up with a lot of memory and you have a lot of time on there. Because sometimes compiling these word embeddings, Glove is actually a little bit faster, a lot faster, almost half the time. But Word2Vec, if you're making your own word embeddings, it can take 14, 15 hours. And if you're using Glove, it can end up eating up gigabytes and gigabytes of RAM. So if you're making these embeddings yourself, it can become a real problem and a performance bottleneck, both for how do I keep feeding my model, and also how do I apply it, let's say, in a real-time situation. So what some folks in München have been studying is the ability to create dense word vectors and dense document vectors. And they created this idea of densify. And what they were able to see, I don't know if you can see over in the corner, but they were able to get it from English, where it's 4 executions per second, to the densified model at 178 with only a slight difference in accuracy. So the more solutions we find for sentiment analysis, the more problems we have. And depending on, especially if you're working in different languages, this can get even more difficult. What some people are doing that is interesting is attempting to do aggregation within lexicon. So if I aggregate everybody speaking English in this particular city, what they're finding is maybe there's more agreement within that community on sentiment and words. So that's something to look at. I also haven't seen a lot of studies on ensemble methods, and I think that that's coming into vogue, as well as character level embeddings. So character level embeddings are the idea that we can predict and attune ourselves on a character level given a language. So here is a graphic I made. It's very tongue-in-cheek, and sorry if it's a little small. But this is like my own version of Andreas Müller's scikit-learn flowchart, which basically says if you have movie reviews or any reviews, you're set, and if you have anything else and you don't have money and time and samples, you're pretty much screwed. So sorry about that. And I'll post this as well. I'll go back. So have we solved sentiment analysis? Not really. But if you have time or are willing to work on building a lexicon, particularly for your model, what they've found is that there can be some really great wins. So I've found a lot of papers and also a lot of companies that are building their own corpora and their own lexicon, and they're achieving in the 90th percentile. So I want to say thanks. You can reach out if you have any questions. I'll be posting the slides so you can read all of the papers and look at the code that I referenced for the LSTM, as well as the CNN and the simple model architecture.
All right, everyone, we have time for 2 or 3 questions, so who would like a first one? If you want to leave desperately and go and get coffee, please do so very quietly and respectfully. Okay, here we go.
Hi, thanks for the talk. It was great. I wonder if you had a chance to look at Google Sentiment Analysis API they just released this week.
I haven't had a chance to look at that. I do have it bookmarked, but I'll let you know when I do. The problem really is that a lot of these really depend on the lexicon, and Google is likely using their word embeddings, and their word embeddings have problems because everybody else is also using their word embeddings for sentiment. So I would doubt it's massively better than what's available from Stanford, which is generally in the high 70s%, low 80s. But I'd be curious to see, and if you have done, and have you used it yourself? Yeah. It was a little, there's so much happening, it was hard to keep up with everything and also prepare the talk, so.
Thanks very much for the talk. I'm a linguist by training, so a lot of the examples you mentioned really rely, like being able to accurately tell what the sentiment is really relies on knowing a lot about the context. So how much do you think we can actually expect, how accurate do you think we expect to be just based on the text? Because it seems like people are really pouring a lot of effort and time into making the text models really great, and this is wonderful, but maybe there's just a cap at how well we can do only based on text.
Yeah, I agree to a certain degree to that statement. And basically what I'm curious about is more when we start to look at these dependency models and we're able to detect stance and phrases, that if I'm using a series of phrases directed at a particular object, and particularly if I can do that in a multilingual situation, which people are starting to prove that you can do, that's going to take sentiment analysis really to the next level. Because if I can start to say this cluster of words applies to this object and it's obviously negative or it's obviously positive, then I can start to make a little bit of these leaps and bounds and moving away from just this idea that somehow words around other words. So the better our parsers get, and the more we incorporate the parsers into our models, the better sentiment analysis has gotten over time.
This question way up at the top.
Sorry, thank you. Amazing talk, Catherine. That's really interesting. It seems to me, a bit like the previous question there, this sentiment analysis is really a problem of hard AI, and I wonder whether it's going to be the thing that helps hard AI, or whether hard AI is going to give you the ultimate goal in sentiment analysis. Does that make sense?
Yeah, it does. And I was really, really impressed with some of the deeper learning models that have been coming out of this, and the fact that they're actually having really, really good accuracy with very little training. So there's actually some great papers, and I'm happy to reference them and post them. There's some great trainers of saying, yeah, well, we just decided to play around with it for a month, and we were able to nearly get to state-of-the-art fine-tuned systems. So I really think that deep learning is likely the answer here, and as deep learning evolves, I think sentiment analysis will too, because we've seen what it's done in terms of natural language generation. And if it's making these inroads in natural language generation and we're getting these networks that are able to start to understand what we mean or what we're trying to say, then we can start to maybe predict how we feel. But the problem is the sentiment analysis field is still like very, very much a closed model. Most of the places that are doing it are owned by places where they can't open source their code, MetaMind. And so I think that there's this pressure on us as like open source developers to try and keep up with these things that are happening behind closed doors.
And that's all we have time for, folks, so I think you'll join me in thanking KJAM once more. All right.
some information, but
put these things at the bottom. It's ridiculous. I will get this.
chat?
Hi,
Hello.
I'm Ralph.
Hi, Ralph. Are you all set up already? Have you managed to get the signal out?
Yeah, I have a special kind of, I have a micro or mini USB.
HDMI?
HDMI, sorry. Mini HDMI. Let's have a look. If it works.
So you already have this adapter, which is mini HDMI.
It's my adapter, so.
It's your own one. And with all ports, put it in, fail, turn it upside down, fail again, turn it upside down again.
All right. Hey, it works.
Any audio?
No.
Yeah. All right. How long is our slot? I'm supposed to know that. How long is your slot?
30 minutes. Well, actually, it was 20 minutes. But it looks like 30 minutes, but 30 minutes would be the start of the next slot.
Exactly. So we have 25 minutes.
Yeah.
And then you have to choose whether you want to do 25 minutes or whether you want to do 20 minutes plus 5 minutes of questions.
Yeah, I guess I will do it in 20 minutes and 5 minutes question.
Okay. Have you practiced it? How long does it take?
I don't know. I changed it to 20 minutes.
Yeah?
Yeah.
Okay, so like you feel comfortable with that.
Yeah.
So then I'll give you little warning signs. Shall I give you one at 10 minutes and 5 minutes?
5 minutes.
Just 5?
Oh, 10 is okay, yeah.
We'll give you 10 and 5. And 5 minutes means it's like 5 minutes until the beginning of questions.
Yeah, yeah.
So
All right.
It means, if you go on for 6 minutes, it's fine.
Okay. Actually, Fabio wanted to present something also, just to Fabio, from Anaconda,
Oh no, okay.
from Continuum.
Right.
Okay. There are, I'm not the perfect expert on Python, and he wanted to help me
Oh right. Yeah. So he was going to come and help, like stand with you.
for questions, especially.
Well, look, hopefully we'll still come.
Maybe he was coming.
Otherwise, just make up the answers.
Yeah, I will do that.
Just go,
I'm the expert on
Which one
that.
is better, Python 3 or Python 2? Just go, I've been using Python 4 for about 6 months now. It's Intel preview. It's much better.
Python 4, yeah. Python is a snake.
Yeah, exactly.
You're from England.
Yes, sir.
You have a nice French name, last name. Percival.
Yeah. Yeah, I grew up in France.
Ah, okay.
Are you in France?
I'm French, yeah.
Okay, who's that?
Nice.
Des événements un peu tristes.
Ouais, très triste. Très choquant. Insupportable même. Ouais, Percival, it's a really nice middle-aged name. C'est un nom du Moyen-Âge, ça.
Oui, ouais.
Il y a même un roman, non?
Perceval de Gallois.
Ouais.
Il y avait 2 œufs vies. Dans la cour du roi.
D'accord.
Donc c'est mon ancêtre, c'est certain.
C'est clair, ouais.
Au bout d'un moment, tout le monde est l'ancêtre de tout le monde. Donc
Ah, mais c'est clair. Ouais, c'est probablement les chevaliers de la table ronde.
Et là, de Varny,
Ouais, de Varny, c'est aussi c'est noblesse ancienne noblesse française.
particule.
Il y a une noblesse française.
Il y a un château.
Il y avait un château détruit par les Allemands pendant la Première Guerre mondiale. Maintenant, il y a une ferme dessus. Donc... Non.
Et le talk, c'est sûr.
Il y a un peu de hardware, bien sûr, Intel. Et puis un peu de Python.
Matériaux, il y a Intel, Rostam, plein de trucs dans le... Très actif,
Ouais, on va être de plus en plus actif sur Python parce qu'on fait plein de conférences, surtout sur le HPC, moi en tout cas, High Performance Computing, et de plus en plus les gens font du Python. Nous on avait beaucoup de Fortran au début, et ça baisse. Mais il y a tellement de code encore qui tournent.
Même dans le même pays, c'est ça.
Ouais. Et donc il y a plein de Fortran, mais de plus en plus c'est du Python. Et donc là on va sortir notre propre Python, et c'est pour la High Performance Computing. J'annonce, ouais, ça va sortir en septembre, là on est en phase bêta encore.
Je sais, peut-être que les scientifiques ils le savent déjà, c'est pas un secret.
Ouais, il y en a qui sont sur nos mailing lists, qui utilisent peut-être déjà C++.
Pour moi c'est une surprise. Et de Intel, qu'est-ce que j'ai vu récemment, c'est le travail, on a été intéressé par plein de raisons. Et du kernel Linux. Et ça va être une virtualisation de la machine complète. Mais c'est une virtualisation qui arrête de faire croire qu'on va essayer de faire plein de systèmes opératifs différents. On va faire que Linux, parce qu'il va pouvoir optimiser ce paquet de séquences pour le mettre. Exactement le même kernel qu'on a déjà, donc on va faire plein de choses. De commencer une VM en une seconde.
Ok, je savais pas. Wow, ok.
Mais ça peut peut-être être intéressant pour la HPC.
Ouais, de toute façon, là, c'est Linux uniquement. Le HPC, rien d'autre.
2 minutes.
There we go, folks. It's the afternoon slot, the post-coffee break slot. You might think that this is a slot where everyone's going to be too exhausted and too tired for learning, but actually the opposite is true. Because as you warm up through the day, as you see more and more interesting talks, you're actually building up all of those learning neurons in your mind. And it turns out the final few talks of the day are often the most interesting, even better than the best talks so far. That's going to be in this blog, and I suspect in this room, ladies and gents. Come towards the front if you've just come in. If you sit near the front, the speaker is happier, you seem more engaged, the speaker thinks that you're more interested in their stuff, they get more excited, more happy, they convey knowledge better, you get more happy, and happiness just feeds on happiness, learning on learning, knowledge on knowledge, passion on passion, perspicaciousness on perspicaciousness. Come in, sit near the front is better, it's more comfortable, they have heated seats here at the front, at the back they're cooled seats. Everyone at the back has got a numb bum, everyone at the front is like, oh, this is lovely. That's absolutely true. Come in everyone, come near the front. We're going to start in 10 seconds, so come in, and now come in super quickly and quietly. And please join me in welcoming Ralph de Varny, who's going to be talking about HPC on Intel hardware.
Can you hear me? Or maybe I take this mic. That works? Okay, I can't hear me. All right, good afternoon. Welcome to this talk. My name is Ralph de Varny from Intel, actually more Intel Software, because everybody knows Intel as a hardware manufacturer, semiconductor company, but it's also a very large software company. We are about 15,000 software developers at Intel who develop things from low-level BIOS to up to high-end big data solutions. And my talk today is going to be about high-performance Python on Intel architecture. Actually, I come more from the high-performance computing, which is traditionally, the traditional language is, of course, Fortran, right? Intel, we have a Fortran compiler. Who is using the Fortran compiler? Nobody, that's good, thank you. And okay, normally when I go to high-performance computing specialized conferences, a lot of people still do Fortran, right? Because the code didn't change since 1960. And so it's still running. It's running really fast, and it runs on the latest architecture. But more and more, of course, people do C and C++. But what we saw in the past couple of years, since I'm in high-performance computing, is that more and more people are doing Python. So that's why I'm here, actually. So that's why Intel is in Python. It's no wonder. And for the last couple of years, we also love Python at Intel. And so who here in the room is from high-performance computing or does some kind of high-performance data analysis, data, scientific computing, something like that? All right. Okay, who is using Intel processors? Very good. Who is using GPUs? Don't worry, I will not, I like GPUs also. All right. Okay, so today I'm going to talk first a little bit about Intel architecture, where are we at the moment, and after that I'll go into what are we doing for the Python community to make the bridge between software development and our high performance processors. I will mostly talk about high performance processors like Intel Xeon or Xeon Phi, or even your regular Core i7 in your Mac laptop, not for the embedded stuff. All right. So, wow. What's that? Who knows? It's what? What is it? Xeon Phi. Wow. You can get a t-shirt later from me. Xeon Phi. Who knows Xeon Phi? Who heard about Xeon Phi? All right, half of the room. Great. So this is the latest Xeon Phi. We just released it end of June. It was called KNL, Knight's Landing. That's a code name. We love code names at Intel. So that's Knight's Landing. It has 72 cores. You can count them. Every core has 2 threads, and they're all connected through OmniPath fabric. So we hope it's going to be a really fast system. So how does it look like in reality? So here on the left you have the version with OmniPath fabric integrated. There is also a non-OmniPath fabric integrated version. It's like a small cluster, right? You can imagine this as a cluster with a high performance connect between all the cores. And the good thing is, and the new thing with this Xeon Phi is that it's not anymore a coprocessor. This is the third generation, and until now it was a coprocessor. So you had to plug it in a PCI slot, and then you had to pass all your data through this to this small slot, right? And then it gave you a lot of limitations. So the new one will also have a coprocessor version, but the version we just launched is actually a bootable version. So you don't need a host system anymore. It's the host and the coprocessor in one. So you can boot Linux on it at the moment. It can run a lot more workloads than the coprocessor, right? It has less limitation. It has MCD RAM on the chip, right? 16 gigabyte MCD RAM, which is really fast RAM. And it can run normal IA code. So Python, normally it's IA code. So Intel architecture code is really easy to program. That's why it says programmability. It's power efficient. All right. It has a large memory, can use per server up to 400 gigabyte, 384 gigabyte, and it's really scalable. You can build a cluster out of it. So, like I said, there is a regular version without the fabric, integrated fabric. This is the integrated fabric one, and it goes onto a host. It's its own host processor, right? So you can use it as a regular workstation, right? Currently, we have a lot of customers, software developers who have a regular PC. It looks like a PC, and instead of a Xeon or Core i7, they have the Xeon Phi processor in there. And at a later stage, it will also be available as a coprocessor, like a GPU card. But just to go back to a little bit more of hardware. So in the high end, we have 2 processor families. We have Xeon. Xeon is the regular processor, which boosts most of the servers at the moment. All the cloud, the internet, everything runs on Xeon. And Xeon Phi is our new processor targeted at high performance computing, but also big data analytics and machine learning. And the good thing is it features 72 cores, right, with 288 threads, and it has vector units for up to 512 bits, so it can run AVX 512 extensions, would give you a really great scalability if you're doing mathematical operations with single instruction, multiple data vectorization. And so this is what we have now, and the future will be parallel. We will have still more cores, so at least in the next 5 years, we'll go more cores, more threads, and more vectors. So that's going to be really essential if you want to have performance on with your application with numerical mathematics at least and high-performance computing. Right, and the current version of Xeon is Broadwell, this one here. It still doesn't have AVX 512, it has AVX 2 with 256 bit wide SIMD. The next version will be Skylake with AVX 512 on the server. So what does it have to do with Python? So as a lot of Python developers are using these platforms, they want to use the newest and latest. They want to have performance. Of course, you are paying for all these transistors. Right? If you buy a Xeon Phi, you are buying 5 billion transistors. But if you run a regular Python code on it, you will not use 5 billion transistors. But you paid for these 5 billion transistors. So we want to help you get more performance out of it and use all these transistors especially for production, right? Not for prototyping, but for production. But we are also seeing that for normal coders, it's really difficult to use these high-performance extensions. Even for us, it's sometimes really tricky. So it's really hard to combine Python and those high-performance extensions. So that's why this year, in 2 months from now, we are releasing our own distribution of Python, which will be called Intel Distribution for Python. At the moment, it's still in beta, and it's going to be released in the first week of September. Let me check the timing. All right. So yeah, our aim is to give you, as a Python programmer, easy access to high performance in Python, of course. And so it's based on CPython. We recompiled it with our low-level libraries. For instance, the most important one is MKL. Who knows MKL already? Oh, great. So MKL is always at the forefront of performance. It's always optimized for the latest processor technology. So, and we have been able to recompile it into our distribution, but we are not only using MKL, we are also using other libraries like DAL, which is a new library. It's going to be called PyDAL for data analytics acceleration library. It's also in there, and also we are including TBB for parallel programming. So what is required for making Python performance closer to native code? Of course, in HPC, it's always, you want to have native code. That's why most of them programmers are using C++ or C or Fortran. And here it gives you an example of what's required. So there's a very interesting book that came out 2 years ago from one of my colleagues about high-performance computing on Xeon Phi. It's called High Performance Parallelism Pearls. A lot of people in that book are writing an article about how they parallelize their code in high performance. So we took here a very simple example, which is the optimization of Black-Scholes pricing. Right? It's really easy to parallelize that formula. And if you run it on pure Python, right here it's the number of options, 1,000 options per second that can be calculated. If you use pure Python, you are maybe, for the same time frame, for 1 second, you can have like 100,000 per second. If you move this to naive C implementation, you can have a 55 times performance implementation, with static compilation. But if you really use the hardware, all these vector units, all these cores, whatever is included in the Xeon Phi processor, vectorization, threading, and data locality optimization, you could get up to 350 times more performance. So what are we putting into Python to make that happen for you without having you to code everything in C? So first of all, we are accelerating the numerical packages of Python with our libraries, right? MKL, as I said, DAL, and a little bit of IPP, which is more a smaller scale library. We are implementing TBB for better parallelism, to get rid of oversubscription, for instance, and in some cases also for MPI, if you're using the small cluster version. We are also having vTune, which is a profiler. I'm going to show you quickly what that means. We are also optimizing other extensions in Python like Cython, NumBap, etc. And we are also working on the big data machine learning platform and frameworks like Spark, Theano, Caffe, etc. So what is in there? It's going to be MKL, so I'm repeating myself, but we're also optimizing NumPy, SciPy, Scikit, PyTable, etc. All that stuff you have. I can give you a description of all the really long list about what we're optimizing, what packages. We are providing a specific interface for DAL called PyDAL. It's going to be available through this distribution, and also it's available from Anaconda, so from Continuum Analytics as a Conda package. And of course, we like the open source community, the Python community. It's amazing now. I really like this community. It's amazing what happens here. And we, of course, we want to bring all the good things back to the community. And we, in the end, eventually, we are going to also optimize all the other packages of Python. So a quick overview at MKL, what is in MKL. So at the moment, for the first version, we are going to include BLAS, LAPACK. We are going to include multidimensional FFTs, some vector math, and RNGs, which are random number generators, very strong random number generators, which can be used in like Monte Carlo simulation. Here an example of what can happen if you use our beta version of Python. So this is a FFT implementation. You can see on the right side a comparison. If you use regular Python, if you change it with 1 thread or 32 thread, you can get up to 10 times acceleration. Same if you use vanilla Python here, on 1 thread or 32 thread, can get up to 5 times acceleration. Okay, random number generators. Don't know if it's interesting to you who use random number generators. A few. So we really can get very nice results on random number generators, right, up to more than 50 times more performance than regular Python. Okay, DAL is optimized for machine learning and statistics and big data analytics, so it has a lot of components, and we are currently working on really making that available through PyData, through a real Python library. So let's have a look at vTune. vTune is a low-profile, it's a low-level profiler. Who is using vTune or who knows vTune? vTune is an old product from Intel, which we make current every year. It's mostly used by C programmers, C++, Fortran, to find hotspots in the code, right? Where is my hotspot? Where is my application running slow? Is there any performance gain I can implement? Am I using all my cores, all my threads? Am I really using the processor at low level the right way? It's a very visual tool. It's low. It uses not much of the performance, right? And it can give you visibility up to the code, right? To the source code. So it pinpoints the source code where your hotspot is. That worked until now in C, C++, Fortran, but we made it also available on Python, because up to now, if you would use Python, it would show you the C code of the library, so that was not the intent, right? So how it works, here you have some Python code. It's something very simple. We have two routines. One is slow and one is fast. That's easy, right? And we want to see if vTune is able to run at the same time as this small program and find the code that is slow, where we know which is slow, right? So we start it. It runs at the same time as your code. It can even analyze the performance measurement units, the PMUs in the processor, and see what's happening in the processor directly. And so it shows you here, this is the result. It's very visual. normally you have it on a much bigger screen, so this is a small screen. And it shows you where in your code the hotspot is. So here, slow encode, surprise, it's here, right? Fast encode is okay, it runs fast. The slow encode runs slow. And if you click on this, you'll get directly to the Python source code. So that's the goal. So vTune is now available also for Python and recognizes Python code. And vTune is really a low-level profiling tool which doesn't use a lot of overhead, like 1.1 to 1.6, works on Windows, Linux, and can use Python 3.4, 3.5, all the versions basically. It's really a rich graphical user interface. I would not say it's easy to use, but it's, we try to make it intuitive more and more. It supports different workflows, so you can start your application, start vTune at the same time and wait for vTune to end and analyze the results, or you attach it to an application and you only profile a certain area of your code. All right, so that's the end of my talk. I still have 30 seconds. So you can download our version of Python at the moment from Intel Software, software.intel.com. It's still in beta, like I said. In the beginning of September, it's going to be released. It's really supporting the full stack for high-performance computing and big data, machine learning, whatever. All right, thank you very much.
Thanks very much, Ralph. Any questions?
In the latest processors, you are starting to embed FPGAs. Do you have something of that? Yeah. Yeah. So, yep.
Yeah, so the question was about what about FPGAs? Intel bought Altera a few years ago, and since this year it's part of Intel Altera, and our plan is, of course, to put some FPGA technology in our Xeon processor going forward. Right? At the moment, I have nothing specific to say about that. It's still in the works.
You mentioned machines that have the Xeon Phi as the main processor. Who's building these?
Who's building these?
Yeah. Where can I get one?
You
That's
can
a
get
question.
one. So you can go to your local OEM and order them, so they can take orders. At the moment, on the market, we have the software development product. So the one I said, it's like a workstation. You can buy it from Colfax or from a German small OEM. I don't recall the name now. So you simply go on the Xeon Phi webpage and you have the list of, there are two small OEMs who build this workstation. You can order them. It's like $6,000 one workstation. But other than that, if you want to have more information, you have to go to HP or Dell, and they are building currently their offerings.
The Intel distribution for Python is only for the Xeon series of processors, also for others?
It's for Intel architecture. So you can use it on Core i3 or in a laptop.
i3, i5?
i5, it's all the same, basically. Core i3 is basically the same as a Xeon E5 or Xeon Phi. The configuration is different, but the basic architecture is the same. That's why it's really good for programmability.
More questions? We have a couple more minutes. There you go. So I'll have one. So the basic idea of the special Intel Python distribution is that you've just taken the exact same CPython source code and you've just compiled it with different flags which again are magically optimized the way Python works, or you then have to also rewrite things like NumPy slightly to...
No, as far as I know, I'm not the full Python expert, we recompiled C Python using our low-level libraries like MKL, DAL. So you should not, I'm not promising anything, right? Don't record me now. Yeah, it should work out of the box.
Thanks.
It's compiled with ICC, right?
It's
compiled with ICC, right? The Intel compiler.
That's the plan, yeah.
Okay.
So ICC is the Intel C compiler, C++ compiler. It's our C++ compiler. We optimize it to the maximum, to what is doable, and we of course use it for ourselves in this case. But we also work with GCC, so we also optimize GCC. It's not that we love the open source community.
No, the question is if I have a library that's compiled with GCC, if I have any issues with interfacing to it from the ICC compiled Python.
So theoretically, the ICC and GCC are binary compatible. So you should not have any problem. You can mix codes from both with both compilers.
Any more questions? We probably have time for one more, so it might be the best question yet. There you go. It will have to fit into 45 seconds, including the answer. 42 seconds.
So one thing, the distribution is free. Of course, it's free. It's not open source. It's free. The MKL is not open source. It's our proprietary library. But the distribution will be free to download, free to use, and with community support. If you want premium support from Intel, you will have to pay, and through the Intel Parallel Studio package.
Great. Well, then, will you join me in thanking Ralph? Thank you very much. Okay, the next talk starts in 5 minutes.
All right, merci.
Thank you very much indeed.
Ouais. Ah ouais. Non. Python, non, mais...
Sorry, real questions here. I was asking the FPGA thing because myself, I'm a training engineer, HCL and all those things. Although I'm more on the ceilings, but I'm actually working on porting the OpenWRT to the FIC and things like that have a processor and a proper system and
Yeah.
FPGA. So
Okay.
I was actually asking if you were doing some processors with FPGAs.
Well, that's the plan, right?
Yeah, no, the idea is if you actually had some libraries or...
At the moment, we are using the Altera stuff.
Oh, okay.
Yeah.
Until it gets...
Yeah, it's not easy.
No, it's not.
Wow. Programming FPGAs, wow. And then programming...
It's easy to program.
Yeah, but doing
Yeah,
both.
but to do
Yeah.
both,
This is not gonna be easy.
Yeah, okay. No, I was just... Okay, thank you.
You're welcome.
Good. So, what are you talking to us about? You know, I'm secretly, I know the answer to this, of course. So, what is it? Oh, yeah. Shared graphic architecture, I remember that. Good. Have you tried plugging in yet?
No.
Okay, let's do that. You have audio?
No, not really. Just me.
Alright, fine. That's your HDMI, and then there's a VGA.
Right. Let me quickly check before you do this.
I've got secrets on that. Yep. Always with some paranoia that secret emails appear. Good. So you've got them, because you're lucky, you have the second stop, so the full half hour. And how much would you like to use for questions?
Yeah, so we'll finish at 4:45, so we'll have 15 minutes to get live talk, so there should be no rush. No, I mean, so after the first, I'm going to show you warnings at like -10 and -5. Would you like them to be leaving 5 minutes for questions or leaving 10 minutes for questions? Then they can always ask you afterwards. Yeah. Okay. So when I'm going to show you the warnings in 10 minutes, it means you have 10 minutes left until we begin questions. So it's 10 minutes to do stuff. If you want to run a little bit, that's no problem. Cool.
Welcome everyone, we'll start in a few seconds. Take your seats. Seats at the front are the best seats, as we all know. Like, sit right there in the front row and the speaker will feel like you love what they're saying and are super engaged. Or if you're worried that the speaker is going to spot your knobbly knees, you can hide one row back, that's good too. There you go. So here we are, going for the last talk of the day, which is every single time, in my experience, the best talk of the day. Please join me in waking our speaker to talk about shared nothing architecture.
He is right, by the way. It is the best presentation you'll see ever. So, thanks everybody for coming. I'll be here sharing something with you today about shared nothing architecture, which is ceramic in itself. Before we kick off though, I want to thank my employer, Binder, for making it able for me to be here and talk about this to you guys. Yeah, so shared nothing. Those are two words. What is it? In essence, shared nothing means nothing more than sharing no resources. So all you do is make sure that everything that you run runs on its own CPU, memory, or disks. You know, any program that you have does that and that alone. It became a very large thing back in the day. I think the first written thing about it is 1983, which is older than I am. But the good thing about it is that you can make separate units of programs. So you can separate your concerns in a way that anything you write does its own thing on its own hardware and doesn't do anything else, which is super useful. Also, it makes you able to scale things independently. So, for example, if you run a website, you can deploy your own code in some way. If you get a lot of requests on, for example, just your HTML pages, you can scale those servers up and leave the rest as it is. Or if you do a lot of processing on the back end, you can scale that up and leave the front-end service at where they are. Also, it's very resilient against outages. A good example for this is, for example, Netflix, who made their own Chaos Monkey thing. Who here has ever used Chaos Monkey? Okay, so if you've seen it, you're probably well aware of how it can kill your entire network and your entire application, but not if you set it up correctly. And last but not least is loosely coupled. So every little thing can die on its own and then it can be restarted and something will take the features over as it is. More interesting though, shared nothing doesn't mean you share nothing. Lots of things still, especially in the web sphere, if you have a web application, you will be sharing state. People will be logged in, will be authenticated. you'll be in a certain state of a process. Workflows in your application will be shared all over the entire thing. And people don't generally do that in one request. So every step you take, you got to go on further and further. And additionally to that, because you have all these separate units of things, everything depends on each other in some way. So where would you do shared nothing? Easiest reason is, as I said, fault tolerance. Anytime your application has a problem, it can deal with it itself. Your entire architecture is built to make sure that that thing can get back to where it was or get back to a state where it will actually work. It's scalable. As I said, you can scale independently, and it leads to much more smaller and simpler applications. Very good example for this is that you can build an application that just does what it does. Welcome. But the best thing about smaller applications, as you're probably well aware of, is you can test them better, you can manage them better, you can review the code better, you can do anything you want with the code that you have, and you can explain it better to other people. So also if you transfer the project or hire new people to work on it, it's just much easier to get to a certain point where it's useful to use. It does have some considerations. You're going to be simplifying your code base, you're going to make smaller, simpler applications, but if you oversimplify, you're going to make a problem larger instead of smaller. If you do crazy things like have an entire Python application, you make every function a salary task, everything is going to be slow as balls because it's only communicating over the network with your backend and hoping to get an answer at some point, and then all your servers are doing nothing else but communicating to each other. So that's not a good thing. Also, you need to know when you need to start. If you're just making a weblog, like any WordPress website or anything like that, if you're going to separate those things, you're wasting a lot of time and you're not making anything more useful than it really is. Other than that, you also require a lot of infrastructure. Instead of just having one server that does what it is that you do, you're going to need a whole bunch of servers. You need something to manage your traffic, you're going to need something to relay messages, you're going to need something to do all the functions that you have. And as I said before, because there are simple units, simple smaller units, you're going to have just a whole bunch of things that do their own thing. You cannot share the server with any other feature that you are building. So your login page server, for example, cannot suddenly also do the authentication if you do it in the wrong way. And apart from that, you're still sharing state, so you still require a source of truth. I know that databases are one of the origins of shared nothing, but it's Achilles' heel. You'll be storing stuff in there and you'll not be able to scale that in the same way as you can do with your application. This goes for your databases, but also for your caching layers, for example. So where would you be using shared nothing? I know two very good examples of a shared nothing website. One is Google. I'm pretty sure you all know what Google is. If you don't, please raise your hand. Or Binder, which is where I work, obviously. It means at scale. It just means that we do a lot of things. It's everywhere, it's all over the world, it's all working in cooperation with each other, and as I said, it's very scalable. Obviously, data warehousing is also an option by virtue of sharding your data. I'm going to skip that one, but I wanted to list it because this is where it all came from. So what are you going to need to build it? It's an empty slide because I'm sharing nothing. Anyway, first you're going to ingest the traffic. You're going to get traffic from your clients, your users. They need to get to your application. So this is basically your load balancer or any web server that you have. I want to make it more tangible, so we got an example for this. We use Nginx. When this gets the message, it just passes it on to the application server, which we call the front-end application. This does nothing more than gets your request, hacks it into pieces, and determines for itself what it wants to do and how it needs to do that. So because I'm branding things anyway, we use Pyramid for this. Pyramid is pretty awesome, but you could also use PHP or Node.js if you're so inclined, or anything in Go if you're been to those kind of talks today. What it does though, it makes new tasks, and those tasks need to be executed, and the only way to get that done is to insert a message queue into the stack. So there's a message queue. It does nothing more than get a message and give it to somebody else. So for example, we use Celery for this. It's not necessarily just Celery. We run it on Redis, for example, but you could also be deploying it on RabbitMQ or any other things. And I heard somebody talk about OpenRQ recently. Maybe that's fun too. I haven't checked it out yet. And then in the end, you end up with a whole bunch of servers on the rear of your application stack, and it's the backend processing. This can be literally anything that can read messages from your message queue. We use Python things, we use Go, we use Java, anything that you come up with. So this is a bit abstract, so I want to give you some examples on how we do things. Here is a login page. This is our application. It's fantastically beautiful. And you can log in. So you don't need a lot to generate this, so this is a very simple thing. And the stack will basically look a bit like this. You only go to ingest traffic, you go to the front-end application, that decides, okay, I'm going to render this template and give it back, done. Nothing else is needed. Obviously, there is some back-end stuff going on, like storing your session key in the database or in the Redis thing, and making sure all those things are right, but you know, I'm just trying to keep it simple. I also have a less simple example, literally. I uploaded a picture of my daughter in Binder. And this is a slightly more complex operation. I mean, we've all probably made some web application where you upload a picture, but in our case, we store it directly on Amazon S3. So what we do is we ask the web server for a token so that we can upload it to S3. Then when we're done, we tell the web server that we're done. And that moment it decides that it needs to check if the file is actually correct, or if the file is actually an image and not a video, or I would like to know all the information that's in the EXIF data that's in the picture. That's all back-end processing. So there we use the entire stack. So in this case, the front-end application would tell the back-end stuff, please give me everything back from this image, identify it, make sure it's really an image, not a vulnerability or whatever. When that's done, it asks the server to generate a thumbnail, then it generates a web version, then it generates any other type of image that we've requested that it should do. And that, of course, our application is fantastic, so you can configure all those things. But it is asynchronous. It goes back from back-end processing to the message queue, then it goes back to back-end processing, and it goes back to the front-end application. In the end, though, you get a fantastic picture of my daughter in the application, which is what everybody wants. Yep. So what you end up with in the end, and this is the official picture that we share with people, is this crazy architecture. You could tell we're kind of deep into Amazon, and I don't mind really. But you can see that the entire stack is divided into a lot of things. There's a lot of things going on, and everything is separated. For example, we use just the normal load balancers from Amazon to relay the traffic. That's our ingestion. Then we do some web application firewalling, which is also one unit doing separate things. That relays traffic to the web instances. That does some things, and then there's a little arrow going up to a message broker, and all the way at the back are all our processing things. We've only drawn 6 boxes, but there's a lot more. And obviously, because we're pretty cool guys, we do this all with automated deployment for our DevOps people. That's actually a thing I forgot to mention. One other pro of doing this kind of system is that your DevOps people get a lot more Jenkins jobs to do, which they apparently like. I'm going faster than I thought, but that's okay. So in the future, because scaling is still a thing that you need to do. Shared nothing remains extremely effective, especially with all the tools that you have from Amazon, for example, or Google, or OpenStack delivers. It's super easy to deploy an entire shared nothing architecture anywhere in the world. However, there's a new thing coming up called serverless architecture, where you can essentially do a lot of things about anything really. Instead of deploying your servers and you're managing your own hardware, or you're worried about CPU and memory, you can just deploy some code, and that also works. I'm not a fan though, because I like getting my fingers dirty with system operation things. So I stick with shared nothing. However, serverless architecture, if you can get into it, is a fun thing to check out. Now, this guy just pointed the 5-10 minute plate at me, but I'm actually at the last slide right now, so thanks.
Short, to the point, and very efficient. I love it. First question here.
You mentioned that you use Celery to distribute the tasks that have to be done. How do you integrate to have asynchronous execution with serving requests, which need to maintain connections, etc.?
You mean that when you do a Celery request, you gotta wait for the result to come back to you?
Yep.
We try to avoid that kind of system, purely because when you are doing that, you gotta make something block in your entire stack, and that's not the most efficient way to get there. So what we try to do is we tell the user, okay, it's coming, and then the front-end application starts polling, or it gets a notification from, okay, this is done, please pick it up.
So you use no WebSockets?
Sorry?
You use no WebSockets or stuff like that?
We could, to give the message back at some point, but I don't really like having an open connection to a server that can die at any second. So I'd rather go for long polling or server push.
Cool. More questions? Yes. Ow. Oh, my leg.
Hi. Thanks for the talk. Maybe an answer for the previous question will be a pusher room, a room in pusher to communicate back with your clients or something as an idea. And I have a question about the broker you are using for Celery.
Mm-hmm.
Can you give me a little bit of details about the different brokers, or what have you found about it?
So you're asking if what kind of different brokers there are, right?
What are you using, or why are you using the broker you are using? And because I have very similar architecture in my project, and I'm dealing with that right now.
Okay. Not really sure. We use Redis because we like Redis a lot, and we already have it available anyway. But there are other brokers that make a lot of sense when you're starting to scale up. I try to remove layers as much as I can, but for example, a thing like RabbitMQ is very good to use if you want something with more control, or if you want to say more things to the applications using it.
More questions? How about up at the back? The exciting zone for questions usually. You've got a little bit more of a contemplative stance, standing a bit further back. It gives you more of an opportunity to formulate an insightful or possibly a stupid question. There's prizes either way. What about up the front? Oh. Okay, question number 2. There's definitely a prize for that.
So you have mentioned that you use Amazon as a backend. Have you actually tried any other cloud provider, like Google Cloud or Azure?
Yes, we tried. And internally, we're looking at getting into OpenStack just for our internal environments. But for our production stuff, AWS is very useful to us. We are in a deep strategic relationship with them, so we're not going away from there. But obviously, we look around. We see what's going on, and we use some other providers that I'm not at liberty to say, to use certain things from. For example, your backups, you wouldn't keep those at the same location as your production clusters, so that's where we go elsewhere. Just out of academic interest, though, we try to play around and see if we can deploy on other things whenever we can.
All right, any more questions? Fine. All right. Well, then that lets us end nice and early. So you've got. Oh, wait. There is. Brilliant. Here we go. Thank you, sir.
Just again about salary. What kind of guarantees does it provide? I mean, is it exactly every message is delivered and so executed exactly once, or at least once? Or what?
I don't know the gritty details, but as far as I understand, when you just get a message out of there, at some point you have to sign it off as well, that mark it as complete. I think that's a thing that salary manages for you, but I would assume that works. We don't see drop messages at least.
Any more questions? So I have one, I guess.
Surprise.
So, you could go for an option like you've done. You can have a 3-layer architecture where you go, oh, I don't want to spend too much time doing loads of work in my application server. I'm just going to farm off that job to a celery queue, and then I can update the user when the bits are ready. Why bother? Like, why not? So, that means that you can scale your application server and your celery servers separately, but at the end of the day, you've still got to do that computation. So what are the real advantages of saying, okay, rather than having 3 application servers and 20 celery servers, why don't I just have 23 application servers? I can still do all the client-side kind of polling by using individual view. I can upload my image in one view, I can resize it in a different AJAX request, I can request a thumbnail in a third AJAX request, I can request the metadata in a fourth one, and so on.
The main answer, that one lies in the simpler applications kind of thing. So when you build a smaller, simpler application, there's a lot less to check. It's easier to verify, it's easier to test, it's easier to deploy. And the function that you did just has one exact responsibility, and that is doing what it is to do. If you say, I'm going to put everything in the application server, you suddenly have a whole large code base with separate tracks to getting there, making sure that the code operates well with each other. You cannot build changes in one system that will have no effect on the other. I think it makes life simpler if you just pull them apart. And when you ask a thing, say, can you say A, and it says A, and it will never say B.
Okay.
Does it help?
Actually, on more, you can, to continue his answer, you can optimize services. So for example, if you have a shipping service, if you had everything in the same application, you would have to, for example, if you are using Python for everything, you either have to go with C binaries. But if you could actually change the backend and say, this other service is specialized, it's written in assembly, and I don't have to maintain it, but it's super effective.
Any questions rather than answers to questions from the floor? Anything else? Rack your brains, everyone. Here's our speaker. He spent loads of time preparing his slides. In that case, that's the end of our session. We've got lightning talks at 5 o'clock, chaired by some annoying idiot, and I'll see you all there.